Thank you so much for that very, very generous introduction. I'm going to talk about how we can reshape human-AI interaction around societal disagreement. And to demonstrate why this might be a good idea, I think we need to look no further than ChatGPT, just one really exciting example of recent progress in human-AI interaction. And so up at the top here, in a natural language prompt, I've asked it to write an ode to computer science. And already this is really cool. So again, I work in human-AI interaction where we have these foundational visions of designing interactive systems in which humans and AI work together to solve problems, of empowering users to design and train their own AIs, and of how we might trade off agency and automation. But ChatGPT also highlights a growing challenge in human-AI interaction, which I focused on in my dissertation research, which is that increasingly we are using AI for problems where what qualifies as a good answer is going to depend upon who you ask. And to get at that challenge, I want to try a slightly different prompt here, which is write an ode to the most important sub-area of computer science. And so what happens here? Well, it begins, oh, artificial intelligence, how vast and grand thy field, where algorithms and models make the future yield, and goes on from there. Now again, I'm a human interaction research, so I happen to think that both HCI and AI are pretty important sub-areas. So I'm not sure I'm totally on board here. And more broadly, this is a task where people might disagree about what the right answer ought to be, right? You and I might have different priorities here. And that task was just one example of how user-facing AI is increasingly moving from a domain in which there was sort of little to no disagreement about what the right answer ought to be to domains in which there might be enormous disagreement about what the right answer ought to be. So for instance, in medicine, when specialists disagree, there are entire tumor boards that are set up to sort of discuss and debate diagnosis and treatment approaches. In design, closer to my own field, different designers might have very different ideas about what that AI ought to do. You know, if you're a sort of Bauhaus designer, you're thinking pretty differently about a visual design problem than someone who comes from a different design school. Or in social computing tasks like content moderation and misinformation detection, clearly people are going to have very different ideas of what acceptable behavior looks like online. And in this talk, I'm going to focus on what I'm calling societal disagreement. So these are decisions that impact multiple people or stakeholders in the face of competing goals and values, where it's not just about what I want, but also what other people want. So that might be content moderation, where we're making decisions that impact the health of entire communities. It might be creative tasks, like designing a poster, or even designing this talk, where I was trying to reason over and optimize for how different people in the audience might respond to what I'm saying here. Let's take content moderation as an example used to address hate speech, misinformation, harassment, radicalization, even just enforce community-specific norms. Moderators, researchers, engineers all want classifiers for these critical social computing tasks so they can easily deploy at scale. But in content moderation, different communities online can have vastly different norms and values. That's true both across communities, and that's true within communities, where Reddit moderators disagree with each other on 29% of removed posts. So when we're using AI to help keep communities healthy, you know, whose labels, whose perspectives should the model be emulating? Today, the existence of multiple perspectives is largely sort of hidden away or treated as noise. And so as a result, AI often solves the wrong problems, behaves in unexpected ways, causing societal harm. But I think that rather than thinking of this as a sort of problem for AI, we can actually treat it as a sort of opportunity. I think we have an opportunity to create human AI systems that help us adapt new perspectives and expertise towards our goals. So how are we going to do that? Well, this is an example of a kind of problem that I find really interesting. I think that the exciting challenge of working in human AI interaction is that to really make progress, we have to sort of bridge design principles that we get from HCI with the modeling realities of machine learning. And it's not going to be enough to simply sort of wrap some interaction around an existing model like a black box. And I'm going to get at those realities of machine learning in a few minutes, but let's start with some principles of HCI. In particular, I'm going to build on this idea of intelligence augmentation, which is a vision from the 60s of how machines might help us solve problems by making us smarter. And so how do we create those tools? Well, Simon and Norman talk about how representations shape our thinking. They shape how we consider problems and how we solve them. And so in order to sort of reason over the trade-offs and perspectives in these disagreed upon tasks, we have to be able to represent them. And so fronting the power of problem representation here, I'm going to argue that by embedding representations of people in society into our interactions and models and metrics that power human-AI interaction, we can reshape AI into a tool for thought that lets us reason over and evaluate models under societal disagreement. And just to provide an intuition for what I mean here, we can go back to our ChatGPT example with this ode. Today, to create that system, we'd start with some data, which we then use to train a model, which then produces some output. In the case I just showed you, that might be determined by the annotators who did the instruction tuning. But now in this talk, what I want to do is sort of open this black box of training data up and articulate that there might be a series of different perspectives inside it, and then provide you with the tools to actually control those voices, and in doing so, change the behavior of the AI. So, for instance, you might care about how undergrads or PhD students or faculty might have written that ode. And over the next 40 minutes or so, I'm going to sort of unroll that insight over the machine learning pipeline. I'm going to focus first on what we can do in terms of the interactions and the models that we're building. To do that, I'm going to present an interactive AI architecture called jury learning, which enables developers to explicitly reason over whose voice a model ought to emulate through the metaphor of a jury. And then I'm going to ask, what if we can't change the model? At the very least, is there something that we can do at the sort of evaluation stage that helps us become sort of more aware of the problems that disagreement can cause? I'm going to talk there about the disagreement deconvolution, which is a metric transformation, showing how in abstracting away the individual people that models emulate, current metrics can dramatically overstate the performance of many user-facing ML tasks. Well, let's start with how we're going to design these human AI systems that navigate societal disagreement. And so to unpack what's going on here, what we do about it, I'm actually going to start at ground truth. So ground truth is, of course, the stuff that we use to train AI classifiers. And it's incredibly consequential because today, it's how we represent our goals and values in these systems. So imagine you're training a model to remove toxic comments online. Should this training example here, which is making some aggressive comments about pizza and politics, should that be an example of content to remove or keep up? Well, that's a tough one. It turns out that in the public data set that we took it from, around half of people feel each way about this comment. And so in today's typical supervised learning pipeline, we then model a sort of aggregate pseudo-human, predicting typically the majority vote label, while ignoring the annotators who disagree with that majority. Or maybe you could do a bit better and decide that your AI should predict, say, a 40-60 distribution. But if you're a practitioner who's then got to decide whether you're going to remove that comment or not, what do you do with this information? There's not really a good answer here other than just siding with the majority. And for a long time, that majoritarian approach mostly made sense. So, tasks like, is this a cat or a dog? I would argue these tasks tend to operate at the sort of perceptual level of our systems. There's not this sort of higher level cognitive reasoning going on. So, you're hopefully going to say, this is a dog. Otherwise, I have some issues with my own perceptual systems. But when this disagreement is irreconcilable, when it's endemic to a task, who we sample for the labels is going to matter. But again, today, once we've chosen our data set's annotators, whose voice the model then emulates is often left implicit in that data collection and training procedure. And so if we can make that voice explicit, then we can empower practitioners to choose from and reason over the decisions that different people and expertise would make here. So what are we going to do here? How are we going to do that? Well, going back to my thesis statement, I think our goal should be to embed a representation of this problem directly into the interactions in the models. And to do that, I'm going to introduce a system called jury learning, which is an interactive supervised learning architecture a technical and normative approach that lets practitioners interactively explore and tune and shift the behavior of a classifier by explicitly articulating which voices from your data set the model emulates in what proportion. Where you would now specify a jury. It can be any size. Here I'm just drawing 12 because 12 people fit on the slide. And you say what proportion of that jury should represent each group or intersectional identity that you care about. And to make this interaction possible, we're actually going to sort of tease this back apart such that the AI's task is no longer to predict a single ground truth, but to take every annotator in your data set or every or juror here, and then to predict their individual responses. And then we can aggregate that as a result to create a classification decision. And so this really sort of changes the semantics of how the AI works in a way that we think is fairly straightforward and interpretable. And so the output of a system here carries a different kind of interpretation than your traditional classifier. So essentially there's something explicitly stating for the following jury composition, here I'm just giving an example, 56% of people agree this comment is toxic. And so now the AI is being very explicit about whose voice is listening to. All right, so now just to give an outline of where we're going here, I'm gonna trace jury learning through the following stages. So first, our normative goals, then interaction, our technical approach, evaluation, and finally, some implications of the jury metaphor and opportunities. Let's start here with our interaction. So why do we use a jury metaphor? Well, we wanted an interaction that makes it clear that there's going to be a group of individual decision makers from which a single decision must emerge. And we think that a jury is a useful metaphor for this. In fact, what I want to claim is that every data set already has a jury. And what I mean by that is every data set already has some existing distribution of annotators whose voices make up its classification decisions. So in the example that we've been using, these 5 annotators here make up its jury. But today, this is an implicit jury. It's sort of baked into the training data and then swept under the rug. And so the interaction that we've created is really our version of a juror selection process. We want practitioners deciding who these decision makers are going to be in a way that's explicit and visible and easily changeable. And so now let's walk through our jury learning architecture for this toxicity task. And so given an input, practitioners start by defining a jury composition, selecting from characteristics in their data set. So for instance, if a data set contained each annotator's political leanings, the practitioner might select, for instance, 2 liberal jurors. We'll also choose here 2 jurors who are parents with high school diplomas. Juries can be any size. Here I'm just choosing 4 because 4 work for this simple example. And so we now have these 4 empty juror slots. And we need to choose individual annotators from our data sets to fill them. And so we're going to start with all the annotators in our data set. Again, these are all real individual people. And just like in any typical data set, they've each only annotated some small subset of the examples in the full data set. We can now filter to all of the relevant annotators in our data set. Jury learning currently requires that data sets contain these explicit labels about annotators. We can then randomly select a matching juror from the data set to fill each juror slot. And the AI then predicts how each individual juror would vote using all the data that we have about their annotations and the annotations of other similar jurors, giving us this jury's verdict. And I'll talk more about the model architecture that powers this in a minute. And of course, this can work with regression 2, where you predict a numeric value instead of yes or no class. But now just randomly selecting one set of jurors, that's going to give you an idea of what one particular set of people might think. But jury learning enables something impossible with real-world juries, which is that we can actually resample our jurors many times, creating many parallel juries. And then each parallel jury has its own predicted verdict. And so this approach actually results in a direct measure of uncertainty, which is how often the outcome changed across our jury samples. We get this distribution here of jury verdicts, and each dot is a resampled jury. And then for a single final decision, we can take the median, giving us a median of means estimator. And to safeguard against overgeneralizing a whole group's opinions from just a few people, what's often called the atomistic fallacy. The system warns you that, for instance, if you selected the characteristic doctor, but your data set only has a few doctors, you really first have to go collect data from more doctors. And by modeling individual annotators, we've also enabled interactive sense-making about the nature of disagreement. So for instance, we can plot where all the selected jurors fall among their whole population's distribution, helping us prevent the ecological fallacy in which you might assume that all individuals in a group are the same. And so we can really ground the jurors here as individual people with specific characteristics, which enable some other explainability-related information as well. So you could, for instance, start with our distribution here of juries, select then a specific jury, and then display information about a specific juror, which allows practitioners to, for instance, reflect on how that particular juror might have labeled similar inputs in the training data, or look at that particular juror's modeling error rate over all of their test examples. Okay, so that's interaction, but now walking back to this prediction step. How can we predict each annotator's response to some unseen example? Well, we're going to assume that we have a typical classification data set. Each of these jurors are, again, just annotators. And like a typical data set, we assume that annotators have some mostly disjoint, occasionally overlapping set of examples they annotated, and a bunch of training examples they didn't annotate. And of course, we have this not just for annotators that we selected as jurors, but for every annotator. And for every annotator, we have a bunch of characteristics. And then what we want is to predict each juror's response to some unseen example. So how do we tackle this prediction problem? Well, some of you might have noticed that this structure is starting to look a lot like a collaborative filtering problem, like what you use to create a recommender system. So just like how Netflix decides whether all like a movie because you like a movie, we might predict whether all find a comment toxic by whether people similar to me find it toxic. But we have one additional complexity here, which is that unlike Netflix, essentially every inference, every prediction is on a comment that's never been seen by anyone in our data set before. Every inference suffers from what's often called the cold start problem. And now that is a standard assumption in most classification problems. Classifiers are designed to generalize to unseen examples. But in a recommender system, it means that we needed to use what's called a hybrid approach and rely heavily on content features. So to do that, we started out with a deep and cross network, which is a hybrid architecture designed for sparse web scale data sets by Google. But given how heavily we needed to rely on our content features, it was helpful for us to not just sort of train our content embeddings from scratch, which is what was typically done today, but to instead start our content embeddings off with a pre-trained large language model, and then fine-tune that within the recommender system from there. So essentially what this is doing is sort of borrowing the same pre-trained models used for classification and NLP, and then integrating them into a hybrid recommender system. And so on a technical level, how does that perform? Well, I want to start with one kind of cool observation. So if we go all the way back to this sort of traditional aggregated task that we talked about at the start of the talk, where our goal is to predict this gray label at the bottom, it turns out that our model architecture can actually do that a lot better than a typical state-of-the-art classifier. So the x-axis here is mean absolute error. The top bar is for standard state-of-the-art classifier. The bottom bar is jury learning. Lower is better. And so why does jury learning do better here? Well, I think this finding highlights the sort of inherent instability of the traditional approach, was that the value of that gray label was really going to change based on who the annotators are. And so when we make predictions based on who the annotators are, and then aggregate, then we can do better than if we tried to directly predict aggregated labels. So that's some thoughts on the technical side. But now let's talk about the user side, because really our motivation in creating jury learning was that by providing these levers, by asking people to make their values explicit, you're often going to get a more diverse representation in who's making decisions. And that's exactly what we saw in our field evaluations. We recruited 18 moderators from Reddit and Discord. We gave these moderators a jury learning interface and asked them to compose a jury that they'd want to use in their community. And we can then compare the existing distribution of annotators in our data set, what we've been calling this implicit jury, to the juries that moderators chose to create. And what we can see here is that, for instance, in terms of racial representation, they certainly do represent a much broader cross-section of society. And these moderator-composed juries, they behaved differently. They made different predictions than a standard aggregated classifier. And those predictions changed for some of the most contentious and divisive issues when it really matters whose voice you're listening to. We found that 14% of classification decisions change. And these comments in the edge cases, these comments in the edge are really important because behaviors in edge cases tend to become de facto platform policies. So this approach also enables some cool opportunities. For instance, we can easily spin up different juries conditioned on the particular content or situation. So, yes, you could compose different juries for different online communities, but you could also, for example, compose a jury consisting of medical professionals whenever health-related content comes up. Another cool opportunity, counterfactual juries. So we can ask, if the jury that I composed says this comment is toxic, how much might we need to change the jury composition by to flip that outcome? We can set that up as a quadratic program, solvable via convex optimization, and that allows sense making on I thought, given the composition of this jury, clearly they would have found this toxic, but they didn't. So what's going on here? All right, and now sort of taking a step back here, important to make clear that while we view jury learning as a step forward, it's by no means a panacea. It's going to create or sort of really bring previously hidden problems up to the forefront. One challenge, jurors can have biases. So for instance, if you select a medical doctor, there's a small but non-zero chance that you'll get someone who's spreading misinformation about vaccines. Our perspective here is that there's really two orthogonal and complementary worldviews. So today, most approaches assume that the world is broken and then try to apply post-hoc statistical transformations to de-bias model outputs. Now with jury learning, we're saying that it could also be really useful to select or train the people whose voices should influence the model. And work in social science and HCI tells us that it's often more tractable to do the latter. A second consideration, who determines these jury compositions? Well, again, every data set already has an implicit jury. And what jury learning does is make that fact explicit and visible and easily changeable. It's providing this new way to communicate and debate whose perspectives are being included. We think that practitioners should make their compositions transparent so they can be discussed and debated. Finally, it's just important to note that this jury metaphor is not an isomorphism. We wanted, again, this crisp way to communicate that there's a group of individual decision makers from which a single decision must emerge. Then we have some notion of a jury selection process. Practitioners decide who these decision makers are going to be. But there's definitely a tension here between what jury learning does today and what juries offer in practice and legal systems. We view that tension as a feature, not a bug, giving us a path to reflect on the existing literature on the biases and challenges of juries. So for instance, we're now working on tools and methods for participatory determination of the jury. We've also been thinking about deliberation within juries. All right, now moving forward, I've been really heartened to see that over the past year or so, since we first started publishing in this space, AI researchers are increasingly rethinking disagreement. For instance, AI researchers thinking about misinformation and toxicity, data annotation, evaluation approaches, explainable AI, have all cited jury learning. Concurrently, we've seen new technical approaches for modeling individual annotators. But perhaps even more exciting to me is that jury learning could also create new opportunities in human-computer interaction. So for instance, in a project led by my lab mate Michelle Lamb, we were able to use the jury learning model architecture to create interactive systems for empowering end-user audits, which you're seeing a video of now. And while so far I focused on content moderation, I think that this idea that we can be designing interactions that empower end users to control whose voices our models emulate, I think that extends far more broadly. So for instance, if you're using a generative artistic co-creation model like DALL-E and ask it to generate an astronaut riding a horse, it clearly matters which artist, which school of thought the model emulates. Another area, translation. While translation is sometimes an exact word-for-word match, often different people might translate the same sentence very differently. So which translator should your model emulate? Summarization, imagine asking a Republican versus a Democrat to summarize a news article. Even captioning an image for visually impaired users. These are all spaces in which I think we can be designing these new interactive systems that help us make explicit, carefully considered choices about whose voices our models are emulating. Okay, so we spent some time talking about what we can do about disagreement on the data model and interaction side. I want to move down this pipeline to evaluation here. What does societal disagreement mean for evaluation? And here's what I want to ask. So jury learning is this ambitious new approach. It requires rethinking how we collect our data sets, how we train our models. But what if the model is fixed? What can we still do about societal disagreement when we're creating human AI systems? I'd posit that one vital step is to at least ensure that our evaluation metrics are not hiding the user experience that these models can actually deliver. And why is that important? Well, my theory of change here is that we will make different product decisions if we realign our performance measures. So how can we evaluate today's classifiers under disagreement? Well, let's start by talking about today's metrics. So same example that we've been using, this common toxicity task, there are cackle competitions and so on. And if you look at the Rock AUC scores where 1.0 means perfect, 0.5 means basically random, these things look like they're doing really amazingly. 0.95, this isn't quite like class grading, but it kind of looks like they're getting an A here. But in reality, these classifiers appear to be a study in contrast, where on the one hand, we have our metrics telling us that we're almost maxed out on this task. On the other hand, we have audits and press articles and our own eyes telling us that we're really struggling, that there's maybe a lot of users who are not happy with how these classifiers behave. And so it appears that something implicitly perhaps is not being captured here, that maybe there is a sort of dark matter that we're not observing. And now, over 30 minutes into this talk, you likely have a sense of where I'm going with this, which is disagreement, specifically that today's common metrics flatten opinions into a single ground truth, label per example, incorrectly ignoring disagreement. And just to give a super simple demonstration of this, let's say that 2 people said a comment was toxic and 3 said it was non-toxic. Metrics that aggregate via majority vote would assign 100% accuracy to a classifier that predicts non-toxic. But if we were measuring user-facing performance, we would never say here that 100% of users approve. We'd report that 3 approved of the system response and 2 did not. And so specifically what I'm going to demonstrate is that 0.95 Rock AUC score is inflated, as are many scores in social computing tasks. We're going to show you that that specific score should actually be closer to a 0.73, which is this much less convincing number. And the technique I developed to do this is called the Disagreement Deconvolution. And the idea is that we should be able to transform any of today's standard classification evaluation measures to better represent how classifiers perform under disagreement. So can we kind of create a twist that brings us closer to how HCI has learned to evaluate systems? And how are we going to do that? Well, going back to my thesis statement here, instead of measuring predictions against some aggregated pseudo-human, we're going to directly embed a representation of individual people into today's ML metrics. And so intuitively, what you'd want here, and if you agree with me thus far, this shouldn't be a very scary claim, is that we should be comparing predictions to each annotator's belief, essentially inserting one label per annotator into the test set. So in this case, now if a classifier predicts toxic, it'll receive a score in accuracy of 0.6 because 3 annotators agree with that prediction and 2 annotators disagree. In fact, there is no way here to get a 1.0. The best you can do is 0.6. And of course, we could then compute almost any existing popular metric using this new test set. And so essentially our approach is to ask not what proportion of ground truth labels does the classifier agree with, but instead, what proportion of the population does the classifier agree with? And our goal in doing so is to incorporate an estimate of how contested each label is going to be into our ML metrics in an interpretable way. But now why did I say estimate here? Well, it turns out that this problem is harder than it sounds. In reality, things are a bit more complicated. We can't just take these labels as is. There are really 2 possible views of labels here. So in tasks like image classification, you might expect that almost all of the label uncertainty is going to come from sort of annotator error. And then the right thing to do is indeed to aggregate the label across multiple annotators, as is standard today. In these more controversial tasks, you might argue instead that there is no such thing as noise. All sort of disagreement in the labels is going to come from unobserved features. And in that case, what we should be doing is called disaggregation, what I just showed you, where you don't average across annotators at all. So you then evaluate models against all these individual labels, acknowledging that no model can achieve this perfect accuracy. Now the reality, of course, is going to be somewhere in between. These contested tasks like toxicity clearly do include variation from personal beliefs, but we also know that some annotations might be noise. There might be misunderstandings, lapses in attention, maybe your office mate knocks on the door while you're labeling data, accidental clicks. Essentially, there is generally a consensus that we cannot take label annotations as strict face value either. And so our approach here is going to be to try to remove these sources of noise, leaving only irresolvable disagreement. So how can we estimate whether disagreement is noise or sincere beliefs? Well, we're going to start with a simplifying assumption. Our idealized model of the world is going to be kind of a generative model. We're going to assume that each annotator has one stable belief. And when an annotator labels an example, we assume that people will generally answer that stable belief, their true opinion, and that's reflected in the labels that they're generating. But sometimes they're going to sort of generate a different answer. Maybe they're more likely to sort of flip their answer on really tough questions, likely to flip on, less likely to flip on easy ones. Essentially, we're going to say that they have a certain probability of flipping away from that stable belief, conditioned on the item, and we're going to call that probability p-flip. And it turns out that if we know p-flip, then we can resample a new test set by adjusting the observed label distribution as if they did not flip at all. And while there's not time to get into all the details of this approach, I want to try to give a brief intuition of how we can find that p-flip value. And so our key insight here is that many crowdsourced data sets already contain the data that we need. And we've developed a few different plugin estimators depending on what the data looks like. So first we're going to use what's called test-retest data. So crowdsourced data sets often do this thing that you would refer to sometimes as inserting attention checks, where essentially you'll ask the same question twice and then see if people agree with themselves. That's what test-retest data is. So now consider some imagined scenario in which we had unlimited test-retest data, in which we asked the same annotator the same question an unlimited number of times, but we wiped their mind each time we did that. Well, from that data, you could then directly observe p-flip. It would be the disagreement rate with their majority label. Now, of course, in practice, this retest data is not unlimited. It's often quite sparse. And so the technical challenge here that I'm omitting for this talk is how we stratify and aggregate that sparse retest data. All right, now second, if there's insufficient retest data for that, then we can actually set this up as a collaborative filtering problem, where we essentially try to predict every annotator stable belief. And then we can measure how often an annotator's observed labels disagree with these predicted stable labels. And so what do we do once we have that flip rate estimate, that p-flip, that estimate of the amount of label disagreements arising from noise? Well, we can then use it to transform our existing test set. So for each annotated item, we can take here the empirical frequency of annotator labels and then adjust it for the effect of noise. This takes the form of a simple noise level subtraction and renormalization to 1. And then given this adjusted label distribution, we can sample labels from it and treat these samples as representing the noise-free opinions of annotators. And when we apply this, what we see is that many classifiers look way better than they actually are when you account for disagreement. So problems that appear solved in reality are really not. So again, here is that state-of-the-art toxicity from before, that 0.95 from the leaderboard. When we adjust it for disagreement, we get that 0.73 I was arguing for. So you go from your sort of straight A to more like a C- here. So current state-of-the-art toxicity claims to be that 0.95, and our deconvolution reduces to 0.73. The next thing I want to point out here is that we can actually do the same thing now, but with what's called an oracle classifier. And what that means is, imagine you had a sort of magic AI that always guessed, quote unquote, correctly, that always guessed what the majoritarian view is going to be. Well, no classifier we are able to show will ever do better than that 0.73. Because even if this oracle, this magic classifier, always guessed that quote unquote right thing, there's a lot of people who are going to disagree with that. And so it turns out that on a technical level, we are basically maxed out on this task, given the inherent amount of disagreement in the population. We're never going to be able to do much better than this. And across a bunch of other social computing tasks, ranging from misinformation detection to adult content detection and so on, we just see these large drops, huge corrections across the board based on disagreement about what the right answer ought to be. But in traditional AI tasks that are, again, more perceptual, like word sense disambiguation, image classification, we get this much softer correction because people tend to agree on what the right answer ought to be. And so what I want to point out here is that even if we can't change the model, simply by paying attention to disagreements, we can at least hopefully really change how we think, and that can help us lead us to design better interactive systems and maybe lead you to use something like jury learning. All right, now with that, I'm going to rest my disagreement case. And so in the two parts of this talk, I've told you how how these kinds of new interactions can help with societal disagreement, how we can design interactive systems that help us explicitly reason over disagreement, how we can create evaluation metrics that reflect the user experience that models actually deliver. And there's, of course, more that we can do here when thinking about disagreements to start to sort of loosen some of these assumptions that our work has made so far. So for instance, people don't always have a single belief. They can be uncertain. They can hold conflicting views. Disagreements aren't all weighted equally. Think social choice theory. And there are new tensions in data set collection here to think about, like how we balance clear task designs while still eliciting sincere beliefs. But really, the point I want to make is that more and more things that we would think of as sort of human tasks, human judgment and subjectivity are now open to AI systems. So as we start moving into these higher and higher level cognition tasks, we're taking these things that traditionally people have done, and we're going to be navigating large design spaces with many possible answers. And if that's going to be happening, then I think our point of view needs to shift from just being right to how do we use AI to help people make smarter decisions. And so coming back to these foundational ideas in HCI, The real insight behind what I'm doing here is not about disagreements per se. It's about sort of reimagining these interactions and models and metrics to create these interactive systems that help make us smarter. And so with jury learning, we reimagine today's supervised learning pipeline as a tool for intelligence augmentation that puts different perspectives and voices at your command. And we adapted a jury metaphor as a representation, both in the interaction and the model itself. And in the disagreement deconvolution, we reimagined how evaluation metrics represent end users. And so thinking beyond toxicity detection or jury metaphors, my goal really in the large scale is to create these human AI systems that empower us to adapt new perspectives and knowledge towards our goals, that help us sort of see beyond our cognitive limits and put those insights to work algorithmically for end users. And to do that, I think we're going to need to continue to really co-design interactions and models and metrics alongside human needs. And I'm interested in designing techniques for human AI interaction, not just for single end users, but when we're using AI across many users, across communities, across society. And so what might that agenda look like? Well, I want to discuss a few different ideas. Starting with the interaction layer, how can we draw on the knowledge embedded in these models to help make us smarter? To me, the most exciting natural next step here is in asking how we can not just model the decisions that different people would make, but also how they make those decisions. So sort of akin to slipping on a pair of glasses. Could a radiologist see what an oncologist would notice about a CT scan? Could a student designer see a gallery of how Bauhaus or modernists or other designers might react to their work? We've actually been talking to some doctors at UCSF who want this exact capability. And so I'm excited to keep exploring how we can model another person's expertise and create the interactive tools that help end users learn from it. Second, creating a science of human AI evaluation. How we evaluate these models is vitally important. And so how can we sort of overcome today's false separation of concerns between the technical performance of a model and the user experience they provide with an interaction? I think there are two approaches here. One approach is to find sort of clever ways to embed the ideas of HCI into today's AI benchmarks. I've done that in the disagreement deconvolution. I also did that in a notes paper called HYPE, which was learning psychometric functions to evaluate generative models. That's one approach. The second approach is about how we can take what we've learned about user-centered evaluation in HCI and sort of amplify that up to the scale needed to iterate not just on UI design, but on models themselves. I think a key to achieving that is going to be in creating formal methods around how we can combine the complementary strengths of human evaluations, which are great at reasoning over these point-wise instances of quality and usability, and automated evaluations, which can reason over a large-scale set of a model's outputs. And then finally, thinking about our data sets and models, one key challenge here: how can we discover the dark matter in our data sets? So much like the jury metaphor, I'm borrowing a physics metaphor here, and the question is, how can we create tools that afford reasoning over not just the existing data, but also tools to reason over what's not yet in your data set, that dark matter that hasn't been observed. So for instance, let's say that you're using ChatGPT to critique an essay, whose perspectives might be missing from a data set used to train that model. And so the question here is, how can we couple human creativity with the power of these recent advances in generative models to discover and start to infill these missing voices, perspectives, and ideas?
All right, break out the vuvuzelas. So, definitely a talk that Mitchell has never given before.
Sorry if it sounded a little rehearsed, but that was my 15th time giving it.
Yeah. So we have a few minutes for questions, comments, disagreements, and anything else.
So with the disagreement deconvolution paper, what is your opinion about these goals that we should reach for? So like you were saying, like even with the Oracle example, like 0.76 or whatever was like the best you could do. Should we like change what like we think as like what the best is, or what do you think about that?
Yeah, that's a great question. So, I think the kind of glib answer here is, well, jury learning is what I think we should be doing. Essentially, what I think we should be doing is, given that there's this disagreement, we ought to first be aware it exists, not hiding it, and then second, be able to make explicit, intentional choices about how we deal with it. That's sort of the vision I'm trying to pitch here, instead of just hiding disagreement as we tend to do today.
I just talk. Thank you so much. This is a great defense talk. Yeah. I guess one question is, first of all, you show this on toxicity. So do you really like require a data set where you have like all these different people's opinions, and so you can really do this fine-grained selection of different voices to represent? And then also, have you thought about how, like within a group, there might be diversity? So like within the perspective of like women, there might be like a lot of different perspectives, and how do you incorporate that?
Great question. So in terms of the data set, so back when we built this tool, this was sort of in the very early, even before the days of, the generative models that we have now. And so at the time, I think the perspective was that yes, we need a data sets that explicitly collect data from different groups or people that you might care about that we can then model. Now, there's lots of recent work at least trying to show that with what we're seeing with these generative models like ChatGPT, GPT-4, et cetera, kind of embedded in them somewhere, different perspectives and ideas. And so I think that's still an emerging space, but it might mean that we might need a lot less data, or at least a lot less sort of explicit data, if we can try to sort of find these different viewpoints within existing models. In terms of different viewpoints in single groups, I think that's super important. That was sort of a key design principle in creating jury learning. And so, for instance, we don't just let you say like there's one or two people from a particular group in your data set. We're going to then put that in your jury and model the opinion, and there you go. We require that you have a lot of people from each group, so that we can then model the entire distribution of those people. We have those sort of plots I was showing, where you can plot individual people in a group against the entire group to sort of see where they fall in the distribution. So I think really important to have these sort of sense-making tools that make it clear what the whole distribution of opinions look like within a single group.
You talked a little bit about the aspects of the jury metaphor that are like not yet realized, but you're kind of thinking about, like the jury selection process. I was wondering if there were any parts of like a jury or the idea of juries that you think are like not worth incorporating into this, like something bad about juries or that like we shouldn't bring into the modeling process.
That's a good question. So maybe just first I'll briefly note that what a sort of jury conception looks like, that clearly depends on like the legal system of the country you're operating in, et cetera. So I'm going to just talk here in terms of like the Western legal system. But there's a lot of great work that has been done by sociologists, psychologists, lots of folks sort of getting into some of the challenges and biases that juries have. I think one sort of key thing that's missing right now is deliberation. So that's one thing I think would be great to add. But at the same time, that's also one area that can really introduce a lot of sort of complexity and bias. And so to me, that's the area that's both the most exciting and the place where you have to be the most careful.
Yeah, I'm curious what deliberation means. Like, are you thinking again of like generative things where you would like actually simulate conversations, or is like there's some abstract way of modeling deliberation? Also fine if you want to keep that under your hat.
No, it's a great question. In fact, a month or two ago, I was talking to someone at DeepMind who was saying that he was currently working on trying to have generative models take on different points of view and deliberate with each other. Now, I sort of, the way that I envision this, is maybe my talk would suggest, is as a more sort of intelligence augmentation point of view, where I think there are really cool opportunities to use these generative models to maybe help augment the way in which we debate with each other, rather than just sort of saying two models should go have at it and decide for themselves. But I think there's lots of cool things to be done in sort of both of those directions.
I'm curious if you have any parting shots for the grad students in the audience, having now finished your PhD, advice you'd pass on to the current students.
The biggest advice has been already said, but I'm going to say it again, which is, for me, it was so sort of important and rewarding, both like intellectually and otherwise, to take on big ideas, to take on these sort of big challenges and attempt to make sense of the world and then execute on them. It can be kind of scary at first, but it was, I think, really worthwhile, and I'm so glad that I did it. And that's what I would suggest other PhD students think about doing as well.
All right, want to close this out?
So Mitchell, you showed us how with the Kaggle competition, the majoritistic objective ended up producing a model that did as well as it could in a more disaggregated metric. Can you describe the scenario where a majoritistic goal would result in a classifier that does not perform optimally by that other definition of success? Does that make sense?
What I was trying to show with the Kaggle thing is that we have a sort of majoritarian viewpoint that made it look like the model was performing really well, but in practice wasn't. And so I'm not quite sure I understand this sort of the point that you're getting at, the opposite of that maybe?
So you told us this model is not performing as well as you think it is, but then you ended up showing us it's performing as well as it can based on this other definition. So what's a scenario where it wouldn't be performing as well as it could based on your definition?
I mean, that's a good question. I think that if you could just use like a worse version of the, go on the Kaggle leaderboard, go down the leaderboard and find like a really bad model, and then that would be already performing, not state of the art. I think the real answer is sort of just like more and more complex tasks that we're trying to do today. Misinformation detection, for instance, is sometimes considered this sort of more high-dimensional or complex task. So I suspect those models might be a case where we're going to see that. But I think that's sort of like a leapfrog game of wherever models are not currently performing optimally, maybe they'll get there eventually, and then they'll start to sort of really exhibit this issue of they're maxed out.
Okay, thank you.
All right, let's thank Mitchell for his talk.
Thank you. Thank you. Thank you.